Chemometrics is the technique of using spectroscopy to get information about a particular chemical's concentration inside of a sample. The problem that we're concerned with in this tutorial is that we've shined some light onto a sample. We're going to call this an unknown sample. It's one that we haven't seen before. And off of it comes some light, and we measure a spectrum. In the name of U for unknown, we're going to call this a vector of numbers U sub lambda. So that's a bunch of measurements at different wavelengths. And then our job in this situation is we have a particular chemical. For the sake of specificity, let's suppose we're trying to measure glucose concentration in a blood sample. So we want to measure a particular target chemical, glucose, and we want to get that number, C sub t, out of this vector of spectral measurements, U of lambda. To keep track of what we're doing, we need a couple of indices here. So one index I'm going to use here is the letter I, and that's an index over pure components. And when I say pure components, what I mean is that the specimen is in truth composed of a certain finite number of chemicals, say proteins and fats and DNA. So the actual sample, if I were to break it down biochemically, I could list a certain number of pure components, and if I mixed those together in the right ratios, I would recover the chemical concentration of the thing that I interrogated with my light. That's what I'm indexing over here. How many actual distinct chemicals are there in this tissue? The second letter I'm going to use for indexing, I'm going to call J, and that's going to have something to do with the chemometric technique. We train our models that we build on a certain number of samples to practice on or to build up our understanding. And so I'm going to call this the index over training samples. And thirdly, I've already indicated a value lambda here, so I'm going to use the subscript lambda to refer to an index over spectral measurements or spectrum elements. Using this language of indexing, if I wanted to talk about the spectra of all the pure components, I could write that as a little matrix here. Here's a little box. Each spectrum might be listed like this, with the spectral information going horizontally. And then the indices of this matrix, I would have lambda spectrum elements, the width, I guess you'd say, of this rectangle I'd index with lambda, and the number of pure components I would index with I. In this case, there'd be 3 pure components. And I would refer to this matrix then of the pure components spectra as capital P for pure components, and then the 2 subscripts would be I and lambda. Let's consider 3 scenarios now. So I've measured U. Obviously, if I want to perform my chemometrics, I have to make the measurement. So there's always going to be a spectrum U that you've measured on your unknown sample, and you're always going to want to get out this concentration. We're going to take you through 3 scenarios where you have to do certain amounts of work up front, and you get certain amounts of information out at the end. So in the first scenario, what we're going to say is that you know all of this spectral information P. You know all of the spectra of the pure components. So you know this pi lambda matrix in its entirety. So that's a lot of work. You have to know what every chemical was in this sample, and you have to take good reference spectra of all of them. Okay, so that allows us to build what we call an explicit model. And we call it that because we can actually make a full, rigorous set of assumptions and model mathematically what's going on here. And what we would say is that the spectrum we measured, U sub lambda, that vector of numbers, it's just a sum, a weighted sum of all of the pure spectra, the pure components, I would call them. So I'm going to sum over index I, sum over all the pure components, and there's going to be a concentration, C sub I. Each pure component has a concentration, and what I'm weighting is each component's spectrum. So I'm just adding together, this reminds you of stuff you would have done earlier in the course where you modeled the tissue's absorption spectrum using the absorption spectra of oxy and deoxyhemoglobin. You had weighted concentrations of oxy and deoxyhemoglobin, same linear algebra here. If we were to write out this expression in vector and matrix notation, I would say that the vector u, which I'm going to write as a u with an underbar to indicate that it's a vector, equals this vector c times the matrix P, which I'll write in a sort of boldface notation. So that would be our model for how the measured spectrum U depends upon the concentrations and the pure components. A true actual measurement of U, of course, would have some noise on it, but we're going to do a methodology where that noise is going to cancel out. Now, when you solve this equation, which we've talked about also this semester, you do a least squares solution and you get an estimate. And what you do is you multiply P by its transpose on the right, and you end up getting an approach that looks like this. We get an estimate of what the concentration vector is. I'm going to put a hat on it to say that it's an estimate. And it's equal to U, the vector U, times the following sequence of P related vectors. P transpose, I multiply P transpose by P, that gives me a square matrix. I then multiply that by the inverse of the P transpose matrix, which is what would be there. And this becomes the least squares estimate of what the concentrations are. Notice I've emphasized that this is the least squares estimate not of only the target chemical, glucose, but of all the chemicals that are present in the sample. You already had to know what all the pure components were in order to measure the spectral matrix P, and now you get out at the end, for your hard work at the beginning, you get the information about all the chemicals at the end. There is a constraint on this, and that has to do with the inverse of this matrix. It has to exist. It has to not be unstable. And I'm not going to prove this, but I'm going to point out that there's a constraint on the inverse, and this is what it is. So the constraint on the inverse existing stably is that P times P transpose has to look like this. The P matrix, just like I drew it over here, you would expect that you're going to have lots and lots of wavelengths, maybe 100 or 1,000 in a spectrum. You might not have that many measurements, that many pure components in the sample. It's actually unlikely that you're going to encounter having that many distinct pure components that you can measure above the noise. So generally speaking, this is a wide and not very tall matrix. So if this is my matrix P over here with dimension lambda here and I over there, if I write the transpose of that matrix, that just means to take the whole matrix and turn it on its side. So here's that transposed matrix P transpose. It has dimension I over here and lambda over here. When you do the linear algebra on calculating P transpose, the rule for the inverse being stable is that the dimension that gets compressed, the lambda, that's the index that will go away when you do this linear algebra here. You'll get a resulting matrix that has dimensions I by I, like that. The constraint that emerges from this is that the number of wavelengths that you measure, lambda, has to be greater than the number of pure components that you have. Greater than or equal to, I'm just writing it as greater than, because in practice you always make lambda greater than I. So that's a constraint, and I'll put a check mark next to that just because that's usually pretty easy to arrange for. Your spectrum usually has lots of elements in it. Okay, but we had to do a lot of work in that situation. We had to measure this entire spectral matrix. We are now going to seek a situation where not as much work is required up front. So suppose we don't know that matrix. But what we do have is knowledge about, you guessed it, some training samples. So I'll draw a little box here and suggest that we have a container with a bunch of different samples. We can measure the spectrum of each one, ... on and on. So we have J training samples, as I said. Remind you that there's J of them. And what do we have as information about these things? Well, first of all, we always have a spectrometer here, so we can take a spectrum of every one of these samples. So we have the full spectral matrix S, J, lambda. So that's a matrix that has J training samples in it, and we have a spectrum for each of those J samples. And we also have a really good chemistry lab, and we know the concentrations of every chemical in every sample. So we have the full matrix of concentrations C. That's going to have an index I because it tells you the pure component breakdown of all the pure components in every sample J. So these are two matrices that we do possess even though we don't have the pure components that are at the base of this model. So we can still do an explicit model in this case. We're going to go back to a very similar explicit model to what we had over here, except now we're going to model these training spectra instead of the unknown spectrum. So our explicit model here is going to be that the training spectra S, J lambda being the indices, equals the sum over all the pure components of the concentration of each chemical in each sample times the pure component spectrum of each of the pure chemicals. If we convert this into a matrix equation like I did here for the unknown sample, this would become spectral matrix S. It's now a matrix, not just a vector, because there's there's J training samples. And that equals a concentration matrix. Again, two indices here as opposed to the one that we had here. So it's a concentration matrix times the pure component matrix. And then there's going to be noise. Now, you can solve this equation by least squares the same way we solved this equation over here. But we have a different thing we're solving for. We're now solving for P. That's what we don't know. So the solution, the estimated pure component matrix P hat, you get that by multiplying this C matrix by a C transpose on the left, and then multiplying that matrix by its inverse. So that ends up looking like this. C transpose C, inverse matrix, C transpose, times S is the estimate of the pure component matrix. So we'll label that the estimate of P. Now that you know an estimate of the pure spectral matrix of all the components, you can actually jump right up to here now and pretend that you were in case number one. You now have an estimate of exactly what you started off with in case number one. So obviously you can then figure out what the spectrum is of your unknown chemical the same way as before. It would be almost an identical expression. It would be that the vector of concentrations of all the pure components in that training sample are equal to the spectral measurement you made, U, and then the formula looks almost identical to what it did before. It's just that you have these hats over all of the P's. I'll emphasize again that all the chemicals are predicted. Once again, we had to have a reference technique that was able to measure every chemical level in every sample. That's a lot of hard work up front. The payoff you get for that is you get the concentration of all the chemicals predicted at the end. What about the constraint on the inverse? Well, in addition to having the PP transpose inverse having to exist stably, which again implies that lambda has to be greater than I, we also have a C transpose C matrix. So what does the C matrix look like? The C matrix would need to be taller than it is wide, in order for a C transpose, multiplying it from this side, to lead to a reduced size square rather than a big sized square. And if we look at the indices of the C matrix, we can see that there are J samples and I concentrations of the pure chemicals. This will be I. This will be J. And this leads to the constraint that J has got to be greater than I. So this is a significant constraint now, that if there are, say, 10 biochemicals whose relative concentrations are varying in an average sample that you're trying to measure, you've got to make at least 10 or 11, preferably 20 or 50 measurements of samples with different combinations in order to have this technique work for you. But you still had to do a lot of work in this technique, you had to measure all of the chemicals' concentrations, and we only want to predict glucose. So the third approach that we want to explore is the one that would be most enticing if you were trying to build a cheap product. And that's if you don't know the pure component spectra, and you also don't have to measure all of the chemicals. So we would still say that what we do have is a container with a whole bunch of specimens in it again. So we've got all these samples that we can measure, ... lots of those. So there's J of those. And we'll still measure their spectra. So of course we have this spectrometer. We can always measure the spectra. So Sj lambda, that's still there. But we only have measurements of glucose, only the one chemical we want. So we only have the concentration of the target chemical C sub T, and we know it for all J samples. So this is just the target chemical measured at all indices J. There isn't a second index I because we're not keeping track of more than just the one chemical. In this case, we have what's known as an inverse model opportunity. We don't have enough information here to use the full model. The full model is that the spectrum is a weighted sum of all the pure spectra. We don't know what the pure spectra are. We neither measure them directly, nor do we measure all of the concentrations that allow us to estimate what those pure spectra are. So we do not have access anymore to doing this. What we do have access to is the knowledge that we have this kind of prediction happening. The concentration estimate is the spectrum you measure times something. So we piggyback onto that from that idea here, and we say, maybe I can build a model that my concentration, my glucose concentration, the target chemicals concentration for each of my J training samples, maybe that can be written as the sum over all wavelengths, of course, of the spectra that I measured of each chemical times something I'm going to call B. This has a name. It's called a regression vector. This formula says that if I measure the jth sample and I take a spectrum of that sample and I take a dot product of that spectral vector with this thing called the regression vector, it will predict the concentration of glucose in the jth sample. Sounds attractive. Now what we've measured the spectra, we have measurements of the concentration of glucose in every sample. So the unknown is this thing in the box, this B. If I write this equation here in vector and matrix notation, I would say that I have a vector C, as I've had before. I have a matrix S, as before, times a vector B. And again, there could be some noise. And I'll notice here I made an error earlier. This capital noise vector here really should have been it was not a matrix, it was just a vector of only one dimension, just like that. Okay, so if I solve this for B, and I'm going to get the estimate of this regression vector B. The math works out. Do the same trick of multiplying this S by an S transpose on the left. Same sort of game we've been playing all along. So I get S transpose S, fat inverse, times S transpose, times the concentration vector. So let's box that out because that's a big thing for us to be aware of, that we've now managed to estimate this regression spectrum, and now that I know what it is, I can estimate what C sub T is. So if I want to figure out what the concentration of glucose is in my unknown sample, what I do is I take its measured spectrum U, and I take the dot product with this regression vector B. That's the relationship that we saw here. Multiply the spectrum by this regression vector. And that becomes my estimate. So I'll give an exclamation point or two to that to say that's pretty powerful. Notice I didn't ever have to use the explicit model. I don't know what the spectra are of all the pure chemicals, but I can still estimate what the concentration is of one chemical, my target chemical, by figuring out the regression vector for that particular target chemical. So that's great. However, constraint on the inverse comes in again. S transpose S. Notice this is the pure spectral matrix where we've got lots of wavelengths and a few pure components. If I were to measure a bunch of training samples, again, I have this very long dimension for the spectral dimension, and I probably don't have that many spectra measured. So the constraint on this starts to be a little onerous. Typically, I think of a spectral matrix, whether it's a training matrix or the pure spectra, this Sj lambda matrix usually is longer than it is tall. So we're looking at a situation that doesn't lead to a stable inverse. If I have Sj lambda transpose here, and that leads to in order for this to be stable, we need to have J bigger than lambda, because if I put all the labels on this here, you can say that when I multiply these spectra together, these matrices together, it's the J dimension that gets collapsed, and I end up with a big matrix, bigger than the matrices that went into making it. That tends to have an unstable inverse. And so this constraint here, J bigger than lambda, says you've got a problem. Usually that's not the way experimental design would be done, and you've got to figure out how to get around this problem. And that is the challenge that we'll tackle in the second video on chemometrics.